Welcome back, everyone. In this video, we're going to finish off our create PEFT model function. So over here, we just enabled gradient checkpointing if it's enabled. And now let's continue. First, let's get the LoRa targeted modules. So we're going to say modules is going to be equal to find underscore all underscore linear underscore names, and we input the model. And now this will detect which layers to inject LoRa into by, remember, using our previous function. So over here, we define this function. Okay, and it tells us which ones can be injected with LoRa. And so that's it. And, you know, we can say print fstring found. And then we can say length of modules found this many modules to quantize. And here, let's just add the modules. So this is going to add some printing for us. Awesome. Now let's create the model. The model is going to be equal to get underscore PEFT underscore model, and we give it in our current model with the PEFT underscore config. But you're like, Patrick, where's the PEFT config? And let's actually create the PEFT config. So PEFT config is going to be equal to LoRa config, and here this is just some configuration that we give our model. R is going to be equal to 64. Remember, this is the LoRa rank. We talked a lot about this, you know, whether it's the trade-off between if it's higher or smaller and how that affects training and accuracy. This is the rank, okay? And now, after that, we're going to say LoRa underscore alpha, and that is going to be equal to 16. And okay, so LoRa alpha is a scaling factor that multiplies the LoRa adapter output before it's added to the frozen weights. So when we looked at the formula, remember we looked at that this was the this is the frozen weights, and A times B were the, you know, the LoRa matrices, and then we had to add this WPT to the product of A times B, and that would give us the W effective. But over here, we see this scaling factor. By the way, don't worry about rank decomposition matrix, okay? Over here, we see this alpha, and we didn't see this in our document when we went through it. And so this alpha, what it does is it basically controls how strongly the LoRa update influences the model. So a higher value means a stronger effect, and we usually add this alpha to stabilize the fine-tuning, avoid overfitting, and keep the updates small. Okay, so that's the only thing that I didn't cover in the original PDF when we talked about LoRa. And that's because technically what we covered was pure LoRa. This is just some optimization technique, okay, to add the scaling factor of alpha divided by R. And R is the rank that we used, which in our case is 64. Okay, so just keep that in mind. This is a parameter that controls how much we want to update, okay, the weights, and so we're trying to not make it as aggressive. Okay, when we do the weight updates, that's why we have this LoRa alpha. After that, we're going to have the target underscore modules is going to be equal to the modules, which we just found over here. Okay, so we're going to be able to insert LoRa into these layers. After that, LoRa underscore dropout is going to be equal to 0.1, and this is just some regularization technique for LoRa, obviously, and it's used during training. If you don't know what dropout is, it's essentially a regularization technique where some of the neurons get dropped so that the model doesn't overfit. Here we're saying randomly drop 10% so that the model doesn't become too dependent on single activations. Okay? Bias is equal to none. We do not want to add any biases. And the task underscore type is going to be equal to task type dot casual underscore language model. This denotes that what we're fine-tuning is a large language model. That's why it's denoted as the casual LM. Okay, now actually we have the model where we get the PEF model. We feed in the model that we have, which was over here, and the PEF config, which we just defined over here. Awesome. And now we will enable mixed precision training. And this will speed up training with very good accuracy, actually. So let's say for name and module in model dot named underscore modules, we're going to say if is instance, and we're going to say that the module is a LoRa layer. And remember, we imported LoRa layer over here at the top, remember? And this is used to identify LoRa injected modules. So over here, we're saying if the module is a LoRa layer, in fact, and if BF16 is enabled, which we will, and we remember we set the flag, then module is going to be equal to module.to torch.bfloat16. And so if the submodule is a LoRa adapter layer, then we convert its parameters to bfloat16 for faster computation and lower memory usage. Now let's come out, bfloat16. And now let's come outside the if statement. So we're over here. If norm in name, so essentially, if the layers whose names contain a norm like layer norm or RMS norm, those are numerically sensitive and should stay in float 32 for stability, okay? Casting them to lower precision like BF16 could cause training instability. Okay, so if norm in name, we just say module dot to torch dot float 32. Okay, and now let's have another if statement. If lm underscore head in name, or we have embed underscore tokens in name. And essentially what we're saying is for the embedding layers with the embed tokens and the final output projection, which is the LM head, that's what we're checking right now. If has attribute, the module has a weight attribute, then what we're going to do is we're going to say if BF16 and module dot weight dot dtype is equal to torch dot float 32, then module is going to be equal to module.to torch.bfloat16. So we convert weights to bfloat16 if BF16 is enabled and weights are currently in float 32. Okay, so over here what we're just checking is if the embedding layers and the final output projections, which are not included in some of these previous layers, so we check them and we essentially say if they have any weights, thus checking if the module has the attribute of weight. And over here we say if BF16 is enabled and the weight has a data type of float 32, we're just going to say, okay, convert it to bfloat16 for us. And so this is the core of mixed precision training, basically, because for some modules, we enable bfloat 16, but for others, where that would cause an issue, we leave it as float 32, okay? So I hope now you understand what mixed precision training is. And I misspelled module here. Module. Okay, and now outside of the for loop, we're going to say model.print underscore trainable underscore parameters. And we're also going to return the processed model. So congratulations, you have successfully created a function that is going to set up the LoRa config and also implement mixed precision training. So let's save all of this, and I will see you in the next video.